So we're going to want to graph all of this. And what we're going to do is we're going to go from left to right and just label everything that we see. So here the 1/4, can you see that that's outside of the function? That's going to be a vertical compression. That's going to multiply your y values by 1/4. Then we hit a 2. That 2 is inside the absolute value. That's going to be a horizontal compression. That's going to multiply your x values by 1/2. The 3 is inside the function. We have a +3. That's going to move it a horizontal translation. A horizontal translation 3 to the left. And finally, the +4 here, that's going to be a vertical translation 4 up. So we're going to look, when we have multiple things, we're going to move from left to right, look at each one in a row, and label what they're going to do. Then when we go to graph this, what they wanted us to do in here was graph each individual thing separately and come up with 1, 2, 3, 4, 5, 6 graphs, or 5 or 6 graphs in the end. That's very tedious and is not what we're going to be doing every time. What we're going to be doing every time is we're going to be thinking about, what does my original graph look like? Well, if I saw this big long equation, I would pull out of that, I see an absolute value. And I know what my basic absolute value graph looks like. And I can draw a quick sketch of it off to the side. So off to the side here, I draw a quick sketch of my absolute value graph. It's got 0, 0. Some other points on here, maybe I label 4, 4, -1, -1. I have lots of points that I could label on there. Now what we're going to do to our original graph is the same thing we've been doing with stretches and compressions. We're going to take the points that we have originally and apply those things to them. So 0, 0 is a key point, and we'll start with that one. What's going to happen to 0, 0? And unlike before, we're going to have 2 sets of arrows. We're always going to have an arrow. The first set of arrows is always going to be all of our compressions and stretches and reflections. Because if you're going from left to right, can you see the first 2 that I run into are both stretches, compressions? And those are where your y values and x values are multiplied by something. So the first arrow will always be what you're multiplying by. We're multiplying y by 1/4 and x by 1/2. Your second arrow will always be your translations, always moving things up and down, left and right. And in this case, we're moving 3 to the left and 4 up. And then we see what happens to the points when this gets done. 0, 0. Multiplying 0 by anything, that doesn't change anything. But 3 to the left and 4 up, we'll change this to -3, 4. Now I have lots of points on my original graph that I could choose. Looking at what I'm going to be doing, multiplying y by 1/4 and x by 1/2, I could choose -1, -1, but then I'm going to be working with fractions and then having to add numbers to fractions. It's not impossible, but why make your life harder when it doesn't need to be? If I choose on my original graph, if I choose 4, 4, or -4, -4, that would be another point on here. -4, +4, sorry. if I choose those points, can you see when you multiply your y-coordinate by a quarter, you'll still get nice numbers to start with? And so what happens to these points? What happens to 4, 4? Well, y value by 1/4 will be 1. X value by 1/2, that'll be 2. Same thing here, but it'll be -2, 1. And then we need to go 3 to the left. So this will be at -1. This one will be at -5. And 4 up. Those will be at 5. I can plot my new graph now. I'm going to have -3, 4. -1, 5. And -5, 5. Since I knew that this point here ended up becoming that point there, that's a key point for my vertex, I know where it's going to end up. So in the end, all of these transformations have taken place. We can combine them together by doing transformations twice. And we'll always do our multiplying first, and then our adding and subtracting afterwards. So let's look at some of the examples on the next page. Here's your original graph of x cubed. They're showing everything all together. They're saying here, what happens if you translate down 2 first and then multiply by 3? Well, you get this equation, y equals 3, I'll write it here bigger so that we can see it, x cubed minus 2. That's kind of written in a different way. Can you see that the minus 2 isn't inside the function? That inside the function is where the x cubed is. Okay? That minus 2 is outside of that function. What's another way that I could have written this final equation? And this is more often when we go to graph things, we'll more often write this as, if I distribute this 3, can you see that this is the same as 3x cubed minus 6? So when we graph this, what we would do first is we would do our vertical stretch first by 3, and then move it down 6. Can you see this endpoint being moved down 6 easier now than if it was written the other way? And here we have another graph. Oh, the graphs just disappeared. But in that one, the stretch factor 3 and then 2 units down. Where did the graphs go? Oh well. That will be more likely how we'll do it in that order. So here's our example 1. We've got our graph. We're going to sketch and label its image after a vertical compression by 1/3 and then a translation of 2 units up. So we're going to take our original points. So on this graph we've got -5, 3. We've got -2, -3. We have 1, 0, and 4, 6. Just to label things here, this is always our stretches first, and then translations afterward. And with stretches, that includes compressions and reflections. This is where we are multiplying by things. This is where we're adding and subtracting things. We'll always do two separate arrows when we have many things to combine. So in this one, we want a vertical compression by a factor of 1/3. That means in our first arrow, the only stretch compression we have is multiplying y by 1/3. And then the second arrow is where we have a translation. That's where we're going to up. So we label those things separately. We can see where are those points going to go. Well, y by 1/3, this will become -5, 1, -2, -1, 1, 0, 4, 2. So we've multiplied each of our y coordinates by 1/3. Then we move everything 2 up. Y value up 2, up 2, up 2, up 2. So we can look, where are our new points? Well, we've still got -5, 3. Now we have -2, 1, 1, 2, and 4, 4. Now imagine our original red graph. Imagine it being squished towards the x-axis first by 1/3, and then translated 2 units up. Does that seem to match with our final graph? So that's sort of a mental check that we do at the end. Do things match up with what we see? Now, for this question, unlike other questions that we do, we are going to do the original one off to the side. It's in your notes, but we're just going to walk through it in the same way. And the reason that we're going to look at it is because, oh, we never finished the last question. Sorry, let's just finish this up. What didn't I do? Oh, it didn't ask me, oh yeah, sketch and label its image. But it didn't ask me to label it with an equation. But just for practice, I'm going to label this with an equation in terms of g of x. So this equation that we have now, that we've got done, if we had y by 1/3 and 2 up, that's all vertical stuff, and the equation would look like this: 1/3 out in front of the original function, and a +2 after. So vertical stuff happens outside of the function. Now, with the one that we have here, with the original question, this is all horizontal stuff. And the reason we're going to do this one as well is because something interesting happens with horizontal compressions and translations when they're put together. Starting it off the same way, we're going to look at our points. We've got -4, 3, 0, -2, 2, 5, and 4, 2. We have stretches and translations here. So it's asking us to do horizontal compression by 1/2. So we're multiplying our x values by 1/2, then 3 to the left, and see what happens to those points. So just a lot of mental math that ends up happening in these questions, and take your time, concentrate, because it's so easy to do oh, I was thinking about doing my x coordinates and I did my y coordinates instead. And you can mess up things so quickly and so easily. So just take your time, really concentrate while you're working on your points. My x values by a half, -2, 3. This one's going to be 0, -2, 1, 5, 2, 2. And then 3 to the left, -5, 3, -3, -2, -2, 5, and -1, 2. Okay? I would recommend not doing your mental math that quick. Slow down. Figure it out. Make sure you're doing the right coordinate each time. Double check it after each one, because this is where these questions will get you. Is subtracting 3 off of -2 hard? No. By any means, it's not hard math to do. And because it's not hard math, your brain is going to be tempted to think about something else while you're doing it, to be like, oh, let's just do this fast and write down numbers quickly and not check them over, and you will make tons of mistakes that way. I know I have. Because this is easy, I should do it quick, I'll get my numbers, and then you plot your points, and they don't look like anything that it should, and you're wondering what went wrong. And then when you try to find your mistake, it ends up taking 5 times longer than it should. So if we take our time while we're doing it, it's going to be better for us. So I'm going to label our points. -5, 3, -3, -2, -2, 5, and -1, 2. Connect those. And now that they're connected, I'm going to say, does it look like it's first been squished towards the y-axis and then moved 3 to the left? My shape seems to say that that looks reasonable. Now, the reason I wanted to show you this one is that when we go to write this equation in terms of f of x, there's 2 things you might think of doing. So I'm going to write 2 of them down. I'm going to write one of them in green, one of them in black. I don't want you to write both of them down, but I want you to think, which one do you think is right? So x by a half, both of these things will be inside the function. So there's my black equation with something inside the function. There's my green equation with something inside the function. X by a half, that's going to show up as a 2 inside my function. 3 to the left is going to show up as a +3. So now here are our options. We could have x +3 like that, or we could have x +3 like that in another set of brackets. What's that? Sorry, the green one. You think the green one is the right one? Okay. Can you see how both of them look very similar? But the green one, if you distribute it, you would get 2x + 6 inside. So they aren't the same. One has 2x + 3 inside. One has 2 bracket x + 3, which if you distribute it would be 2x + 6. When doing a horizontal compression and a horizontal translation, first of all, think about, if you were given this question, which way would you write it? Would you write it the green way or the black way? Because that's the first thing, because this is a place where people will make a lot of mistakes. And now I'll say that the answer is the green one. So if you would have written as the black one, if that's what your gut was telling you, okay, your gut's pretty strong, it will tell you again to do that on the quiz. What happens with a horizontal stretch and a horizontal compression, it's always written in factored form. So I want to make you guys write a note about this at the bottom of your page. You have some space right at the bottom. Just write special note when we have a horizontal, I'll write this in capitals, a horizontal stretch / compression / reflection, any one of those, with a horizontal translation, when those two are together, we must write it in factored form. We must. Wow, it's a new pen. I like it. Must. Perfect. So what we see in this last equation is that it had a horizontal compression and a horizontal translation. When writing that equation, it has to be written in factored form. So to see that +3 to the left has to be in factored form. And when it isn't in factored form, we will factor first in order to see that. Okay, questions to do are 4, 5, and 6.